Okay, so this first example says find the center of mass of a thin plate of constant density covering the region bounded by above by the parabola 9 minus x squared and below by the x-axis. So you can see here I'm bounded below by the x-axis and I'm bounded above by the parabola here. Now I went ahead and drew you a vertical strip right here. Now the center of this vertical strip is actually x units from the y-axis. So therefore the x value of the center of mass is just x. And then the height of this vertical strip can be determined by the distance from the x-axis to the function, which is just 9 minus x squared. And then so we want the halfway point to get the center of the strip. So we take 9 minus x squared over 2 for the y value of the center of mass. Now the length of this strip is 9 minus x squared. Of course the width of the strip we'll just say is delta x. And so that means the area of the strip is 9 minus x squared times dx. Not delta x, but dx. Now the mass, which is dm, is actually the density function times the area. So I take the density function delta here and multiply it by the area, and that gives me the mass. Now, so the moment of the strip about the y-axis, basically to get the moment about the strip about the y-axis, I know that I'm going to have to integrate this y tilde dm, and we know that that y tilde dm would just be 9 minus x squared over 2 times this value up here. So putting that together, and then if we simplify that just a little bit, I get 9 minus x squared times 9 minus x squared, which is 9 minus x squared quantity squared. And then you have the delta and the 2 here. So that's your density function, and then it's divided by 2. And then what we can do next is we can integrate this value to get the moment of the plate about the y-axis, about the x-axis. So get the moment of this about the x-axis, then we just integrate this. And we're going to integrate it from minus 3 to 3 because it intersects the x-axis here at minus 3 and then here at 3. So our strips, goes all the way from negative 3 over to positive 3. So now, again, I'll leave you to integrate this. And so just use the power rule here and then integrate it from negative 3 to 3. And I got 1296 over 10 times the density function. And then I reduced that, I got 648 over 5 times the density function. Okay? And now to get the mass of the plate, I just integrate the dm, which I learned up there at the top that that's just the density function times 9 minus x squared. So we're going to integrate that from negative 3 to 3. And so the mass of the plate turned out to be 36 times the delta there, or the density function. And then the y-coordinate, so the y-coordinate of the plate's center of mass, which is going to be the moment about the x-axis times the mass. So it's the moment about the x-axis, divided by the mass. So the moment about the x-axis was 648 over 5, and the mass was 36. And then you can simplify that, and you'll see that it actually equals 18/5. So the y-coordinate of the plate's center of mass is 18/5, and due to the symmetry, the x value is simply going to be 0. And it's 0 because if you look at your plate is symmetrical about the y-axis, so the symmetry has to lie here on the y-axis, which would be where x equals 0. So, your symmetry might be right here. Your center of mass might be right here, where the x value is 0 and the y value is 18/5. Okay, so that's the point for the center of mass, 0, 18/5. Okay, now we're going to do this example again, but this time we're actually going to give it a density function rather than a constant density. So we're going to say that the density function is 2x squared, and it says it's twice the square of the distance from the point to the y-axis. So that would actually be 2x squared. So now to find the moment, I would do it just like I did up here. But instead of having a constant density function, that I pulled out here, because if you go up there and look, you'll see I had delta over 2 because the density function was constant. But since the density function is a variable, then I have to leave it in the integral. And now here you're just going to go ahead and integrate. Well, first of all, you're going to square this and then multiply it by 2x squared using the distributive property. So I have faith that you can do that. So go ahead and multiply all this out and then integrate it from -3 to 3. And when I did that, I got 11,664 over 35. And then also to find the mass, if you go back up here, remember to find the mass, I had the density function times 9 minus x squared. Well, now I know the density function is actually 2x squared, so I'm going to have to multiply 9 minus x squared times 2x squared and then integrate it from -3 to 3. And again, you can do that. Just multiply those together and then integrate from -3 to 3, and you'll get 648 over 5. And then finally, to get the y-coordinate of the plate's center of mass, then that y-coordinate, y bar, would be the moment about the x-axis, which is 11,664 over 35, divided by the mass of the plate, which is 648 over 5. And then if you reduce that, you get 18 over 7. And then again, due to symmetry, the x-coordinate is just going to be 0. So your center of mass point would be x equals 0 and y equals 18/7. Okay, on this last example, we're going to find the center of mass of a wire that has constant density that's shaped like a semicircle with radius A. So here's the wire, and actually in this example, we're going to model the wire. We're going to say that y equals the square root of a squared minus x squared. Now again, due to the symmetry, we know that the x bar is 0. So really all I need to look for is y bar. Okay. Now we're going to approach this a little different. So I want you to imagine the wire divided into these segments here. These triangular looking segments here. Okay. And where the length of the segment here, this length from here to here, is actually ds. And actually, since we know that the length of a sector is actually the radius times the angle, we can say that ds is a times d theta, because d theta is this angle right here. So the length of the segment is going to be ds, and when I say segment, I just mean this piece from here to here. It's just going to be a, which is the radius, times d theta. And then the mass is simply the density function times ds. So that's density times a d theta. And now to get y bar, we integrate this y tilde dm, and to get that, we can see that the y tilde, we're going to integrate from 0 to pi, and that, in other words, we're going to let theta go from 0 angle all the way over to pi. So that would go from, that would make the sectors go all the way around. And then we're going to integrate that a squared times the density function sine theta d theta. Now let me tell you where the sine theta comes from. If you want the distance of the center of mass to the x-axis, that would be the y value, and you know this y value right here can be determined or written as a sine theta, because this point right here is actually a cosine theta times a sine theta. So the y value, the distance the y value is from the x-axis, is a sine theta. So finally, we put all that together. Now that we know that y tilde is a sine theta, then we take a sine theta and we multiply it by the dm I had up here, which is the density function times a d theta, and we get a squared times the density function sine theta d theta. And then down here, we're going to go ahead and integrate the dm, and we'll get the integral of a times the density function d theta. Now, I'm going to let you go ahead and integrate this. So go ahead and integrate this. Now remember, the a squared and delta are constants. So really you just integrate the cosine and you'll get sine theta, and then you evaluate that from 0 to pi. And then down here, you're going to evaluate this. I'm sorry, I said that wrong. I've already integrated sine theta and I got minus cosine theta, but now you evaluate this from 0 to pi, and then in the denominator, when you evaluate a delta d theta, you simply get a delta times theta, and then you evaluate that from 0 to pi, and you'll get a value there. Now, after you evaluate both of these and then divide and cancel the common factors in the numerator and denominator, you should get that y bar is 2a over pi. So therefore the center of mass actually lies on the axis of symmetry at the point 0, 2a over pi. And of course, so if you knew what the radius of that semicircle was, then you would actually have a numerical value for this point. Okay? All right, I'm going to leave you with this last paragraph, and I'll go ahead and read it to you here. It talks about centroids. When the density function is constant, it cancels out the numerator and denominator in the formulas for x bar and y bar. Thus, when the density is constant, the location of the center of mass is a feature of the geometry of the object and not actually of the material from which it's made. In such cases, engineers may call the center of mass the centroid of the shape. To do so, just set the density function equal to 1 and proceed to find x bar and y bar as before by dividing the moments by their masses. So in other words, it's just telling you that you can set the density function equal to 1, because it really doesn't matter if it's a constant density function, whether it's 1 or whether it's 100, because the densities are going to cancel out when you divide. Okay, so that finishes this section. Let's see what I'm going to cover next. In the next video, I'm going to talk about surface areas of revolution. So earlier we talked about getting volumes by revolving curves around an axis, and we got some of those weird solids and we were able to get the volumes. But in the next section, I'm going to show you how you can actually get the surface area of those weird solids. So see you there.